Hi everyone, it's Sorkin. Today we have a problem when we are given a root of a binary tree and we need to return the smallest subtree that contains all the deepest nodes in the original tree. Okay, and the depth of a node, right, depth of a subtree is, for example, in this case, the depth is 2. And we are given a definition of it. It's the shortest distance to the root. So in this case, for example, for this node, the depth is equals to 2, right? And for this one is equals to 3. Let's take actually this example without these two nodes. Let's say we don't have these nodes, and the only tree that the only nodes that we have are these nodes, right? We have right subtree and we have a left subtree and we have a right subtree. So in this case, what is the depth of the left subtree, right? And what is the depth of the right subtree? So in this case, in both cases it equals to 2, right? This distance 2 and this distance is also equals to 2. So, and then we need to return the smallest subtree that contains all deepest nodes, right? We have 4 deepest nodes, 1, 2, 3, 4, right? The subtree that contains all of them, 1 contains only 0 and 8, and 5 contains only 6 and 2. The node that contains all of them is 3, right? Is 3. So we are returning 3 here. So So what's going to be our algorithm? Our algorithm is that we are going to first check the depth of a left subtree, and we are going to check the depth of a right subtree. If they are equal, it means that we need to return 3, right? Because in this case we need to return the parent, because only in that case it will contain all the deepest nodes. So let's take now another example. Let's say that we have all these nodes, right? So let's say that we have calculated, and now we have the depth of this node right subtree is equals to 2, and the depth of left subtree is equals to, right, this one, right, is equals to 3, right? So is equals to 3. So again, we are now, it means that the smallest one, now we are going to search for our smallest subtree on the left side, because right side is not relevant anymore because it's shorter than the left side. Now we are checking again, we are checking the depth on the right side, and we are checking on the right side and the left side and the right side. So again, in this case it's 1, right? Let's take another color. So in this case it's gonna be 1, right? And in this depth is equals to 2, right? Again, we are searching in the right subtree for the smallest subtree that contains all the deepest nodes. And now we are checking for here, right? Now we are checking for 2. For 2 we are checking, and the depth is equals to, in this case, right, depth is equals to, for the left and right subtree, is equals to 1, right? Is equals to 1. It means that we can return this node, right? If we are returning these nodes, it checks all our boxes, right? In our case, so it contains all the deepest nodes. What are the deepest nodes? Deepest nodes are 7 and 4, right? And the smallest subtree that contains the deepest nodes is 2. Okay, let's first create a tree node parent, right? Parent that will, at the beginning, will be our root. Now let's calculate the depth on the left side and on the left side, left subtree and right subtree. So left is, let's call the function get depth. We are going to implement that in a second. So we are calling our root, right, left, and the same we are doing for the right, and right. So what we are checking that while our left is not equal to our right, So in that case, we are going to implement our logic. And once we exit this loop, once the left is equals to right, in that case, we are returning our parent, right? Because it contains all the deepest nodes, right? So now let's implement our logic. So let's check that if our left, right, if our left is more than our right, then in that case, what we are going to do, we are going to search on the left side of our tree. So our parent is now points to the parent left. Okay, otherwise else is exactly the same but for the right, right? So we are doing for the right. And once we exit this loop, we are calling again so we are calculating our left, updating our left, right? And calling our function get depth and the parent, and the same we are doing for the right. So the same we are doing for the right and the right. Okay, now that's our implementation. Now let's also implement our get depth function. So it's a private, we are returning int, and the get depth, right? It takes our tree node, and if our node is equals to null, then in that case we are returning what? Returning 0. Otherwise we are recursively calling the function. So math maximum, right? Max, we are calling get depth function for the left, right? Node left, and get depth node right, and +1. Okay, as we go one layer lower. Okay, let's run our solution. Okay, great, it works as expected. What is the time and space complexity of our solution? The time complexity is that we are visiting every node, so it's O of n number of nodes, and the size. And how about the space complexity? Space complexity is determined by the stack that we are maintaining here when we are calling the get depth function, right? And the maximum of it is equals to the maximum size of our maximum depth of our tree. So maximum depth, let's put here. Okay, that's it for today. Hope you like my content. If you like it, please hit the like button and subscribe my channel. See you next time. Bye.